Space is beautiful, it's awe-inspiring, but it's trying to kill you in ways you've probably never imagined. And the scary part? Even our most advanced technology might not be enough to stop it. Deep space doesn't just kill you, it erases you cell by cell in ways we're only beginning to understand. And here is a question. If you could teleport anywhere in the universe for 1 hour, where would you go and what would you do? Comment down below. I will pin the most creative answer. Now let's begin. So what exactly makes deep space so deadly? You might think it's the cold or the lack of oxygen, or maybe the terrifying vacuum. And yes, those are problems. But the truth is far more complex and far more interesting. Deep space attacks your body on multiple fronts simultaneously. It tears apart your DNA with invisible particles. It weakens your bones faster than any disease on Earth. It confuses your immune system. It even changes the way your brain works. The universe is vast beyond comprehension. Light from the nearest star system, Alpha Centauri, takes over 4 years to reach us, traveling at nearly 300 million meters per second. Between those stars, between the galaxies, lies a void so empty that you might find only a handful of hydrogen atoms in every cubic centimeter. On Earth, that same cubic centimeter of air contains about 25 billion molecules, but empty doesn't mean safe, far from it. See, deep space is filled with things we can't see, can't hear, and can barely detect. Cosmic radiation screams through the void at nearly the speed of light. Galactic cosmic rays, born in the violent deaths of stars billions of light years away, traverse the universe like invisible bullets. Solar wind, a constant stream of charged particles from our sun, creates an environment unlike anything found on Earth's surface. And when our sun gets angry, when it unleashes a solar flare or coronal mass ejection, it can release the energy equivalent of millions of nuclear bombs within minutes. Right now, as you're watching this, Earth's magnetic field is shielding you from most of this cosmic onslaught. Our atmosphere, that thin blue line visible from space, absorbs what makes it through. But step beyond that protection, venture into deep space, and you're facing the universe's fury directly. No magnetic field. No atmosphere. Just you, your spacecraft, and the relentless bombardment of radiation that has traveled across time and space. Here's what makes me pause and really think about our place in the universe. We are children of Earth in the most literal sense. Every aspect of our biology evolved under specific conditions: gravity, a protective magnetic field, an oxygen-rich atmosphere, liquid water, moderate temperatures. Take away any one of those things and our bodies begin to fail. Take away all of them simultaneously and you're looking at a survival challenge unlike any humanity has ever faced. But before we can talk about solutions, before we can dream about colonies on Mars or journeys to distant star systems, we need to understand the enemy. We need to look at what deep space actually does to human tissue, human bones, human brains. And trust me, what the research shows is both terrifying and absolutely fascinating. Now here's where things get really interesting, and this is something that honestly deserves more attention. Make sure to hit that subscribe button and give this video a like, because what we're about to discuss next reveals just how vulnerable we really are out there in the cosmic ocean. Let's start with radiation, because it's probably the most insidious threat facing any astronaut venturing beyond Earth's protective bubble. We're not talking about the kind of radiation you get from a dental X-ray or even the elevated levels that astronauts experience on the International Space Station. We're talking about exposure levels that would be illegal in any workplace on Earth, sustained over months or years. Radiation in deep space comes from 3 primary sources, and each one presents unique challenges. First, there's galactic cosmic radiation, or GCR. These are high-energy particles, mostly protons and atomic nuclei, that originate from outside our solar system. Some of these particles are remnants of supernovae, exploding stars that died long before Earth even existed. When a massive star collapses, it releases an incomprehensible amount of energy, and some of that energy gets converted into particles that zip through space at 99% the speed of light. Think about that for a moment. You could be hit by a particle that was created in a stellar explosion 10,000 light-years away, millions of years ago. That particle has been traveling through the void of space, through dust clouds and past other star systems, carrying energy from an event so violent it could briefly outshine an entire galaxy. And then it passes through your body. These cosmic rays don't just pass through you harmlessly. When a high-energy particle strikes your DNA, it can shatter the delicate double helix structure. Your cells have repair mechanisms, of course. Life on Earth evolved sophisticated ways to fix DNA damage because radiation exists here too, just at much lower levels. But cosmic rays are different. They're so energetic that a single particle can create complex, difficult-to-repair damage. Instead of a clean break that your cells can easily fix, cosmic rays create clusters of damage, multiple breaks close together, along with chemical changes in the surrounding tissue. Research conducted on the International Space Station and during lunar missions has shown us that astronauts receive radiation doses about 150 to 200 times higher than what we experience on Earth's surface. But that's still within Earth's magnetic field, which deflects some of the cosmic radiation. Once you head toward Mars, once you venture into true deep space, that protection vanishes entirely. The numbers are sobering. A round trip to Mars, lasting roughly 2 to 3 years with current propulsion technology, would expose astronauts to radiation levels between 600 and 1,000 millisieverts. To put that in perspective, radiation workers on Earth are limited to 50 millisieverts per year, and that's considered a high-risk occupation. The average person receives about 3 millisieverts annually from all sources combined, including medical procedures and natural background radiation. What does this level of exposure actually do to you? Well, it significantly increases your risk of developing cancer later in life. NASA's current models suggest that a Mars mission could increase an astronaut's lifetime cancer risk by around 3 to 5%. That might not sound like much, but remember, we're talking about one mission. What about people who want to make multiple trips? What about the colonists who might spend years or even decades living on Mars? But cancer risk, as serious as it is, develops over years or decades. There are more immediate concerns with radiation exposure in deep space, things that could affect astronauts during the mission itself. High doses of radiation can cause acute radiation sickness. We're fortunate that under normal circumstances, even in deep space, the background radiation level isn't quite high enough to cause immediate symptoms, but space weather changes that equation dramatically. Our sun is not a calm, steady ball of fusion. It's a roiling, turbulent engine of magnetic fields and superheated plasma. Occasionally, that turbulence creates solar particle events, massive eruptions that send billions of tons of charged particles screaming through the solar system. If you've ever seen the aurora borealis, the northern lights, you've witnessed a gentle version of space weather. Those beautiful, shimmering curtains of green and red light appear when solar wind particles interact with Earth's magnetic field and atmosphere. But imagine experiencing that same phenomenon without the magnetic field to deflect most of the particles, without the atmosphere to slow them down and make them glow harmlessly. That's what a solar particle event in deep space looks like, except instead of pretty lights, you're facing a potentially lethal radiation storm. During a major solar particle event, radiation levels can spike to dangerous levels within minutes. The largest events, like the one observed in 1972 between the Apollo 16 and Apollo 17 missions, would have delivered a potentially fatal dose to any astronaut caught outside during a spacewalk. Even inside a spacecraft, the exposure would have been severe enough to cause radiation sickness, nausea, fatigue, and increased cancer risk. We can predict solar particle events to some degree. The Sun follows an 11-year cycle of activity, with periods of relative calm and periods of intense activity marked by numerous sunspots and frequent eruptions. But our predictive capabilities are limited. We might get a few hours warning before a major event, maybe a day if we're lucky. That's not a lot of time to take shelter when you're millions of kilometers from Earth. The third source of radiation is actually created by the spacecraft itself. When cosmic rays and solar particles slam into the walls of a spacecraft, they create secondary radiation, a shower of particles produced by the collision. Materials like aluminum, commonly used in spacecraft construction, are particularly bad at generating these secondary particles. Hydrogen-rich materials like water and polyethylene plastic are much better at absorbing radiation without creating secondary particles. But water and plastic are heavy, and every kilogram you launch into space costs thousands of dollars in fuel. This brings us to one of the fundamental challenges of deep space travel: shielding. On Earth, we're protected by an atmosphere equivalent to about 10 meters of water above our heads. That's an enormous amount of shielding, and it stops nearly all cosmic radiation before it reaches the surface. To provide equivalent protection in space, you'd need to surround your spacecraft with meters-thick walls of water or other shielding material. The mass would be astronomical, and launching it would be prohibitively expensive with current technology. Some researchers have proposed using the spacecraft's water supply, food stores, and even waste as radiation shielding. By arranging these materials strategically around a central shelter, you could create a relatively well-protected area where astronauts could retreat during solar storms. It's clever, practical, and uses resources you're already bringing along. But it's not a perfect solution. You're still exposed to significant radiation when you're working in other parts of the spacecraft, and the shielding only reduces the dose. It doesn't eliminate it. There's another aspect of radiation exposure that's particularly concerning for long-duration missions: the effects on the central nervous system. Research conducted over the past decade has revealed something unexpected and troubling. High-energy cosmic rays don't just damage DNA, they can also affect brain function directly. Studies on mice exposed to simulated cosmic radiation have shown changes in behavior, cognition, and neural structure. The radiation appears to damage the connections between neurons, the intricate networks that allow different parts of your brain to communicate. Mice exposed to levels comparable to what astronauts would experience on a Mars mission showed signs of cognitive impairment, reduced memory formation, and increased anxiety behaviors. Now, mice aren't humans, and the research is still ongoing, but the implications are sobering. Imagine being on a 2-year mission to Mars, making critical decisions that affect the survival of your entire crew, and your cognitive abilities are slowly degrading because of radiation exposure. You might not even notice the changes yourself, but your judgment could be impaired at the exact moment you need it most. The really fascinating and somewhat frightening thing about space radiation is that we're still discovering new effects. For decades, scientists focused primarily on cancer risk because that's what we understood from studying radiation exposure on Earth. But cosmic radiation is fundamentally different from the radiation we typically encounter. The particles are more energetic, they're different types, and the exposure pattern is continuous rather than brief. Recent experiments on the International Space Station have shown that radiation affects the immune system in unexpected ways. Your immune system is incredibly complex, with different types of cells coordinating to defend against infections, repair tissue damage, and identify cancer cells. Radiation exposure appears to disrupt this coordination. Some immune functions become hyperactive, while others are suppressed. The result is an immune system that's simultaneously overreacting to harmless stimuli and underreacting to real threats. This immune dysregulation could make astronauts more susceptible to infections during long missions. It could slow wound healing, which is already compromised in microgravity. It might even increase the risk of autoimmune conditions developing later in life. And because missions to Mars or beyond would last years, not months, the cumulative effects could be significant. But here's where the story gets even more complex, and honestly, more fascinating. Radiation isn't the only thing trying to kill you in deep space. If you've been curious about just how hostile space really is, I actually made another video exploring the terrifying reality of how dark space really is, and it dives deep into some of the other invisible threats lurking in the void. The link is in the description and on the card above. It complements what we're discussing here perfectly. Now let's talk about something that might seem less dramatic than radiation but is equally devastating to the human body: microgravity. Actually, that's not quite the right term. In deep space, you're not experiencing reduced gravity, you're experiencing weightlessness, freefall. Your body is constantly falling, along with everything around you, creating the sensation and physical reality of zero gravity. Gravity is one of those things we take completely for granted on Earth. It's always there, pulling everything toward the planet's center with reliable, constant force. Your muscles work against gravity. Every moment you're standing or moving, your bones bear the weight of your body. Your cardiovascular system pumps blood upward against gravity's pull. Your inner ear detects gravity's direction, helping you maintain balance and spatial orientation. Take gravity away, and your body's entire operating system encounters errors it was never designed to handle. Within hours of entering microgravity, astronauts experience what's called fluid shift. On Earth, gravity pulls blood and other fluids toward your lower body. Your heart has to work to pump blood up to your brain against gravity's resistance. Valves in your veins prevent blood from pooling in your legs. It's a constant balancing act that your body performs so automatically you've never consciously thought about it. In microgravity, that balance disappears. Fluids shift upward toward your head and chest. Your face becomes puffy and swollen. Your legs, conversely, become thinner as fluid drains away. You might feel congested, like you have a permanent head cold. The pressure in your skull increases slightly, pushing on your eyeballs from behind and potentially causing vision changes. These vision changes, formerly called spaceflight-associated neuroocular syndrome, affect about 2/3 of astronauts on long-duration missions. The increased pressure in the skull can flatten the eyeball slightly, change the shape of the optic nerve, and cause swelling in the retina. Some astronauts return from 6-month stays on the International Space Station with measurably worse vision, and in some cases these changes are permanent. Now imagine experiencing this not for 6 months, but for 2 or 3 years on a Mars mission. The long-term consequences are still unknown because no human has ever spent that long in microgravity. We're pushing into uncharted territory, conducting experiments on ourselves because there's no other way to learn. The fluid shift is just the beginning. Your muscles, no longer needed to support your body against gravity, begin to atrophy. On Earth, if you were bedridden for months, you'd experience similar muscle wasting, but in space, it happens faster and more severely because literally every movement becomes effortless. Pushing off a wall can send you floating across a room. There's no heavy lifting because nothing has weight. NASA has studied this extensively on the International Space Station. Without rigorous exercise countermeasures, astronauts can lose up to 20% of their muscle mass on missions lasting 5 to 11 days. 20% in less than 2 weeks. That's catastrophic. Your heart is a muscle too, and it's not immune to this wasting. The heart actually shrinks slightly in microgravity because it doesn't have to work as hard to pump blood. To combat this, astronauts on the ISS exercise for about 2 hours every single day using specialized equipment. Treadmills with bungee cords that pull you down to simulate weight. Resistance machines that create tension without relying on gravity. Stationary bikes. This exercise regimen significantly reduces muscle loss, but it doesn't eliminate it entirely. Even with aggressive countermeasures, astronauts still lose muscle mass and strength during long missions. And here's the critical question. Will these exercise protocols work for missions lasting 2 or 3 years? We honestly don't know. The longest continuous stay in space was 437 days, achieved by Russian cosmonaut Valery Polyakov on the Mir space station from January 1994 to March 1995. That's impressive, but it's still only about a quarter of the time required for a round trip to Mars. Even more concerning than muscle loss is bone loss. Your bones are living tissue, constantly being broken down and rebuilt in a process called remodeling. On Earth, the mechanical stress of supporting your weight stimulates bone-building cells called osteoblasts. Break down and rebuild stay in balance, and your bone density remains stable. Remove gravity and that mechanical stress disappears. The bone breakdown process, carried out by cells called osteoclasts, continues at its normal rate. But bone rebuilding slows dramatically because there's no stress signal telling your body it needs strong bones. The result is rapid bone density loss, particularly in weight-bearing bones like your spine, hips, and legs. Research from the International Space Station shows that astronauts lose about 1 to 2% of bone mineral density per month in space. That's 12 to 24% per year. To put that in perspective, postmenopausal women who have the highest rate of bone loss on Earth typically lose about 1% per year. Astronauts in space are losing bone 10 to 20 times faster than the most rapid bone loss we see on Earth. This isn't just a matter of weakened bones. The calcium released from deteriorating bone has to go somewhere. It floods into your bloodstream and gets filtered by your kidneys. High blood calcium levels increase the risk of kidney stones, a painful and potentially dangerous condition. Passing a kidney stone on Earth is agonizing. Passing one in space, millions of kilometers from definitive medical care, could be mission-threatening. Researchers have tried various countermeasures. Exercise helps, but it can't completely prevent bone loss. Some studies have tested medications that slow bone breakdown with mixed results. The fundamental problem is that we're fighting against biology that evolved over hundreds of millions of years to function in Earth's gravity. Our bodies simply don't have the programming to maintain healthy bones in weightlessness for extended periods. Now here's where it gets even more interesting and more concerning. When astronauts return to Earth after long missions, they face a grueling recovery process. After 6 months on the ISS, some astronauts can barely stand when they first experience gravity again. Their cardiovascular systems have adapted to not fighting against gravity, so blood pressure regulation is impaired. Stand up too quickly, and blood pools in your legs, depriving your brain of oxygen. You feel dizzy, lightheaded, and you might even faint. Their muscles are weak, their bones are fragile, their balance is completely off because their inner ear has spent months in an environment where up and down had no meaning. It takes weeks or months of rehabilitation to return to normal function, and this is after 6 months in space. What happens after 3 years? How long would recovery take? Would recovery even be complete? There's another aspect we need to consider, something that makes the Mars mission particularly challenging. You can't come home early. If an astronaut on the ISS develops a serious medical condition, they can be back on Earth within hours. There's always a Soyuz or Crew Dragon spacecraft docked to the station, ready for emergency departure. But on a Mars mission, you're committed. The planets align for efficient travel only at specific times. Miss your launch window, and you might be stuck on Mars for another 2 years, waiting for the next opportunity. This means astronauts heading to Mars need to be prepared for medical emergencies with no possibility of evacuation. They need to handle broken bones, appendicitis, dental emergencies, infections, and potentially even surgery with only the medical supplies they brought along. They need to do this while dealing with radiation exposure, bone loss, muscle atrophy, and all the other physiological challenges of long-duration spaceflight. Let me paint you a scenario that keeps mission planners awake at night. Imagine you're 8 months into a Mars mission, halfway to the red planet. One of your crew members develops appendicitis. On Earth, this is a routine surgical emergency. You go to the hospital, a surgeon removes your appendix, you recover in a few weeks. But in deep space, you don't have an operating room, you don't have a trained surgeon, you don't have the anesthesia, the sterile environment, the backup systems in case something goes wrong. Do you attempt surgery anyway, knowing that the appendix could rupture and cause fatal sepsis if left untreated? Do you have someone on the crew with enough medical training to perform an appendectomy in microgravity, where blood and other fluids don't drain naturally? Where keeping instruments and supplies in place requires constant attention. These aren't hypothetical questions. NASA and other space agencies are actively working on protocols for emergency surgery in space because it's not a matter of if, it's a matter of when. The psychological challenges of deep space travel are equally daunting, though perhaps less obvious than the physical ones. Humans are social creatures. We evolved in groups surrounded by family, friends, and community. Even the most introverted among us need some level of social connection to maintain psychological health. Now imagine being confined in a spacecraft about the size of a small house, with the same 5 or 6 people for 3 years. You can't go outside, you can't take a walk to clear your head, you can't escape to a coffee shop or a park when you need space. You're constantly aware that your survival depends on these people and on systems that could fail at any moment. The Earth, home to everyone you've ever known except your crewmates, becomes just a point of light in the sky, then disappears entirely from view. Communication delays make the isolation even more profound. On Earth, we're used to instant communication. You can video call someone on the other side of the planet with barely perceptible lag. But light, the fastest thing in the universe, still has a speed limit. At Mars's closest approach to Earth, about 55 million kilometers away, radio signals take about 3 minutes one way. Ask a question, wait 6 minutes for a response. As Mars and Earth move in their orbits, that delay extends to 22 minutes one way, 44 minutes round trip. This fundamentally changes the nature of communication. You can't have a conversation. You can send messages and receive responses, but the flow, the give and take of real dialogue, becomes impossible. Psychologists have studied analog missions on Earth, where volunteers spend months in isolated habitats simulating deep space conditions. One consistent finding is that communication delays significantly increase feelings of isolation and autonomy. You can't rely on mission control to help with every decision because by the time you explain the problem and they respond, the situation may have changed completely. This forced autonomy is both a challenge and a necessity. The crew has to be capable of solving problems independently, making life or death decisions without consulting Earth. That requires a level of training, expertise, and psychological resilience that goes far beyond current spaceflight experience. The astronauts heading to Mars won't just be pilots and scientists. They'll need to be engineers, mechanics, medical professionals, psychologists, and everything else they might need, all rolled into a handful of highly capable individuals. Research conducted on the International Space Station and during ground-based isolation studies has revealed concerning patterns. Crew cohesion often starts strong, then degrades over time. People develop conflicts, grudges, territorial behaviors. Sleep disruption is common, partly due to the mission environment and partly due to stress. Depression and anxiety symptoms can emerge even in highly trained, psychologically screened individuals. There was a fascinating study called Mars 500, conducted by Russia's Institute of Biomedical Problems. 6 volunteers were sealed in a mock spacecraft for 520 days, simulating a round-trip Mars mission. Researchers monitored their physical health, psychological state, sleep patterns, and group dynamics throughout. The results were illuminating and sometimes troubling. One crew member became increasingly sedentary and showed signs of mild depression, spending large amounts of time in his quarters. Sleep-wake cycles became disrupted, with different crew members on completely different schedules, reducing opportunities for group interaction. Conflicts arose over minor issues that escalated due to the inability to escape the environment. Physical activity levels dropped significantly for some participants, despite the availability of exercise equipment. And this was in a simulation where participants knew they could leave in a true emergency, where they were still on Earth with help nearby, where the psychological pressure was arguably less than it would be in actual deep space. What happens when you add the very real possibility of equipment failure, radiation exposure, medical emergencies, and the knowledge that rescue is impossible? Space agencies are working on countermeasures, careful crew selection and compatibility assessment, regular communication with family and friends on Earth, even with delays, virtual reality environments that can simulate Earth landscapes and provide a sense of escape, structured schedules that maintain circadian rhythms and ensure regular group interaction, conflict resolution training, access to counseling resources. But here's what really gets me thinking about the depth of this challenge. We're asking people to do something that goes against fundamental human nature. Our ancestors spent hundreds of thousands of years evolving on the African savanna, with open skies above and solid ground beneath their feet. The idea of being sealed in a metal can, hurtling through an environment that would kill you in seconds for years at a time, is so alien to our evolutionary heritage that we literally have no instincts or adaptations to help us cope. Every single aspect of a deep space mission requires us to overcome our biology through technology, training, and sheer determination. And that brings us to another invisible threat, one that you might not expect: the spacecraft environment itself. Inside a spacecraft, you're breathing recycled air. The same air circulated through filters and scrubbers, with carbon dioxide removed and oxygen replenished. On the ISS, this works remarkably well. The environmental control and life support system maintains a breathable atmosphere that's actually cleaner than the air in most Earth cities. But it's not perfect, and in deep space, you're relying on these systems completely for years. Any failure, any degradation in performance becomes critical. Carbon dioxide levels need to stay low. Too much carbon dioxide causes headaches, difficulty concentrating, and eventually unconsciousness and death. Oxygen levels need to stay within a narrow range. Too little, and euhypoxia sets in. Too much, and the fire risk becomes extreme. Remember, the Apollo 1 disaster in 1967 killed 3 astronauts during a ground test when a fire erupted in the pure oxygen atmosphere of their capsule. Humidity must be controlled. Too dry and respiratory problems develop. Too humid, and you get condensation on cold surfaces, which can lead to mold growth and equipment corrosion. Temperature regulation is critical because electronics generate heat, and in the vacuum of space, there's no air to carry that heat away through convection. Spacecraft rely on radiators to dump excess heat into space, but if those systems fail, temperatures inside can quickly become lethal. Then there are the trace contaminants. Humans naturally emit various chemicals through respiration, perspiration, and other bodily processes. Materials inside the spacecraft off gas, releasing small amounts of volatile organic compounds. Equipment can leak. All these contaminants need to be filtered out continuously because in a sealed environment, they accumulate. Studies on the ISS have detected hundreds of different trace chemicals in the cabin air. Most are at very low concentrations, well below levels considered harmful. But what about long-term exposure over 3 years, What about synergistic effects where multiple chemicals at low levels interact to produce health impacts? We're still learning. Fire is an absolute nightmare scenario in space. Without gravity, flames behave differently. They form spheres rather than the teardrop shape we see on Earth. They can smolder invisibly, consuming oxygen and producing toxic gases without visible flame. And if a serious fire breaks out in a spacecraft, your options are terrifyingly limited. You can't evacuate to outside, you can't call the fire department. You fight the fire with onboard extinguishers and hope you can contain it before it consumes your oxygen, fills the cabin with smoke, or damages critical systems. The ISS has had several close calls with fire and smoke over the years. In 1997, a fire broke out on the Russian space station Mir when an oxygen generator malfunctioned. The crew fought the blaze for 14 minutes, filling the station with smoke and toxic fumes. They survived, but it was a stark reminder of how vulnerable we are in the space environment. Water is another critical resource that presents unique challenges in deep space. On the ISS, astronauts recycle nearly every drop of water, including moisture from their breath, sweat, and yes, even urine. The water recovery systems can reclaim about 93% of the water that comes aboard the station. It's purified to a level that exceeds most municipal drinking water standards on Earth. But those systems require maintenance, replacement parts, and occasionally they fail. For a Mars mission, carrying enough water for 3 years would be impractically heavy. You absolutely need closed-loop life support systems that can recycle water with near-perfect efficiency. A single person needs about 3 to 4 liters of drinking water per day, plus water for food preparation, hygiene, and other uses. Multiply that by 6 crew members in 3 years and you're looking at tens of thousands of liters. Even with the most advanced recycling, you need backup systems, redundancy, and spare parts to maintain these critical systems over the mission duration. And here's something most people don't consider: dust. In space, without gravity to make particles settle, tiny particles of dust, skin cells, food crumbs, and other debris just float around. They get into equipment, they get inhaled, they accumulate on filters and vents. The ISS has air filtration systems running constantly to capture this debris, but it's a never-ending battle. Long-duration missions would need even more robust filtration and regular cleaning protocols to prevent debris accumulation from degrading air quality or damaging equipment. Let me take you deeper into another aspect of deep space survival that combines physics, biology, and engineering in fascinating ways: the thermal environment. Space itself has no temperature in the traditional sense because temperature is a property of matter, and space is essentially empty. But spacecraft in deep space face extreme thermal challenges. On the side facing the Sun, temperatures can soar to over 120 degrees Celsius. That's hot enough to boil water. On the side facing away from the Sun, temperatures plummet to minus 150 degrees Celsius or lower. That's cold enough to freeze carbon dioxide into dry ice. Your spacecraft experiences these temperature extremes simultaneously, just meters apart. Managing this thermal differential requires sophisticated systems. Radiators dump excess heat into space. Heaters prevent critical systems from freezing. Insulation minimizes heat transfer between the hot and cold sides. On the ISS, which orbits Earth every 90 minutes, the spacecraft constantly moves between sunlight and shadow, experiencing rapid temperature cycles. But in deep space, heading to Mars, your thermal environment is more stable but still requires constant active management. If your thermal control system fails, you're in serious trouble. Electronics overheat and fail. Batteries can't operate outside their temperature range. Water freezes, potentially bursting pipes and tanks. The crew compartment becomes uninhabitable as temperatures swing to extremes. Thermal control isn't a luxury, it's a survival necessity, and it needs to function flawlessly for years. Now let's talk about something that might sound minor, but is actually critically important: Sleep. Humans need sleep. It's not optional. During sleep, your brain consolidates memories, processes emotions, clears metabolic waste, and performs essential maintenance. Your immune system does much of its work during sleep. Sleep deprivation impairs judgment, slows reaction times, and can even cause hallucinations with severe, prolonged deprivation. But sleeping in space is weird. There's no comfortable bed to lie on because lying down doesn't mean anything without gravity. Astronauts sleep in sleeping bags attached to walls or in small crew quarters. You can float, but you need to be tethered so you don't drift around bumping into things. Some astronauts report feeling claustrophobic in the sleeping quarters. Others struggle with the lack of a normal day-night cycle. On the ISS, the sun rises and sets every 45 minutes as the station orbits Earth. To maintain circadian rhythms, the station uses artificial lighting that mimics daylight and darkness on a 24-hour schedule. But even with these measures, many astronauts experience disrupted sleep in space. Studies show that astronauts on the ISS average about 6 hours of sleep per night, less than the 7 to 9 hours recommended for optimal health. On a Mars mission, you'd experience a similar lack of natural day-night cycles during the transit. And the psychological stress, the constant low-level anxiety about system failures or radiation events, doesn't exactly promote restful sleep. Chronic sleep deprivation over months or years could seriously degrade crew performance and health. There's also the issue of noise. The ISS is loud. Fans, pumps, ventilation systems, exercise equipment, all creating a constant background noise level around 60 to 70 decibels, about the volume of a normal conversation or a dishwasher running. Astronauts often wear earplugs to sleep. Long-term noise exposure at these levels can cause hearing damage and adds to psychological stress. Food is another interesting challenge that people often overlook. You might think just bring freeze-dried meals, add water, and you're good. And that's basically what current space missions do. But eating the same limited menu of pre-packaged meals for 3 years gets old fast. Food is more than just fuel. It's comfort. It's culture. It's one of the few pleasures available in a confined environment. Research has shown that menu fatigue is a real problem on long missions. Astronauts start skipping meals or eating less because they're tired of the available options. This can lead to nutritional deficiencies, weight loss, and further degradation of muscle and bone. Space agencies are working on ways to improve food variety and quality, including growing fresh vegetables in space. The veggie plant growth system on the ISS has successfully grown lettuce, radishes, and other crops. Astronauts report that fresh vegetables are a huge morale boost, a taste of Earth in the sterile environment of the spacecraft. But growing enough food to significantly supplement the diet requires space, power, water, and most importantly, expertise. Someone needs to tend the plants, and plants can have diseases, pests, and failures just like on Earth. For a Mars mission, some level of in-situ food production might be necessary, not just for nutrition but for psychological well-being. Imagine being able to harvest fresh tomatoes or herbs after months of freeze-dried meals. That connection to growing living things might be essential for maintaining mental health. Now we need to discuss something that sounds like science fiction but is very real: space debris and micrometeorites. You might think that space is so vast and empty that the chances of hitting anything are negligible. And for large objects that's mostly true, but space, especially near Earth, is littered with debris. Old satellites, spent rocket stages, fragments from collisions and explosions. NASA tracks over 27,000 pieces of orbital debris larger than 10 centimeters. In low Earth orbit, this debris poses a real threat. Objects orbit at speeds around 7 to 8 kilometers per second. At those velocities, even a tiny paint fleck carries enough energy to damage spacecraft. The ISS has been hit multiple times by tiny debris creating craters in windows and requiring occasional maneuvering to avoid larger tracked objects. But deep space presents a different threat: micrometeorites. These are tiny particles, remnants of comets and asteroids, scattered throughout the solar system. They're much smaller and less dense than orbital debris, but in deep space you're exposed to them constantly over vast distances. Over the course of a multi-year mission, the cumulative impact could degrade solar panels, sensors, and other external components. Spacecraft are designed with some level of micrometeorite shielding, typically multiple layers of material spaced apart. When a high-velocity particle hits the outer layer, it vaporizes, and the expanding cloud of plasma is absorbed by subsequent layers before it can penetrate the pressure hull. But this shielding adds mass, and there's always the possibility of a larger-than-expected impact overwhelming the protection. A catastrophic hull breach, a hole punched through the spacecraft's pressure vessel, is every astronaut's nightmare. The air would rush out, depressurization would be rapid, and without immediate action to seal the breach, the crew would have minutes at best to get into spacesuits or reach a safe compartment. This is why spacecraft are designed with multiple compartments that can be sealed off from each other. But here's the thing that really drives home how precarious survival is in deep space. Redundancy has limits. Engineers design spacecraft with backup systems for critical functions. 2 of everything important, sometimes 3, but you can't bring infinite spares. You can't account for every possible failure mode. At some point, you're relying on the hope that catastrophic failures are rare enough that you'll make it through the mission without encountering them. The Apollo 13 mission is the classic example of surviving against the odds. An oxygen tank exploded, crippling the spacecraft's life support and power systems. The crew barely made it back to Earth using the lunar module as a lifeboat, rationing power and water, enduring cold temperatures and rising carbon dioxide levels. They had mission control support, the collective brainpower of hundreds of engineers working around the clock to devise solutions, and they were only a few days from Earth. On a Mars mission, you don't have that support. You are the mission control. You're the engineers who have to diagnose problems and improvise solutions with whatever materials you have available. The phrase "failure is not an option" is inspiring, but in deep space, sometimes failure is exactly what happens, and you have to survive it anyway. Let me share something that really crystallizes the challenge we're facing. In 2008, NASA conducted a detailed study examining the risks associated with human Mars missions. They identified 32 distinct risk categories, ranging from radiation exposure to inadequate nutrition to behavioral health issues. Of those 32 risks, only 8 were considered under control with current technology and knowledge. 8 out of 32. That means more than 75% of the identified risks still need significant research and development before we can safely send humans to Mars. And here's what keeps me fascinated by this entire endeavor. We're still going. Despite all these challenges, despite the very real possibility that early Mars missions could end in tragedy, humanity is pushing forward. Because that's what we do. We explore, we take risks, we venture into the unknown because the alternative, staying confined to one planet forever, is unacceptable to something deep in our nature. But understanding these risks isn't about discouraging space exploration. It's about approaching it with eyes wide open, with the respect it deserves. Every astronaut who volunteers for a Mars mission knows they might not come back. They know they're test subjects in an experiment that's never been attempted before. And they're willing to take that risk because they understand something profound. Becoming a multiplanetary species isn't just an adventure, it's an insurance policy for the survival of human consciousness in the universe. Now let's talk about something truly bizarre that happens to the human body in microgravity. Your spine stretches. Without gravity compressing your vertebrae, astronauts can grow several centimeters taller in space. That might sound fun, like a superpower, but it comes with significant back pain. The muscles and ligaments supporting your spine aren't designed for this elongation. Many astronauts report severe back pain, especially in the first few weeks of a mission, as their bodies adapt. Your internal organs shift position too. Your heart, no longer being pulled downward by gravity, floats slightly upward in your chest cavity. Your intestines rearrange themselves. This doesn't cause immediate problems, but it contributes to the general discomfort and weird physical sensations astronauts experience in space. And we still don't fully understand what long-term effects this organ displacement might have over years rather than months. The cardiovascular changes in microgravity are particularly concerning. Your heart is a pump that evolved to work against gravity. In space, it doesn't need to pump as hard to circulate blood throughout your body. Over time, the heart muscle actually weakens and the heart becomes slightly smaller. Blood vessels lose some of their tone and elasticity. Your overall blood volume decreases by about 10 to 15% as your body adjusts to the new conditions. When you return to gravity, your cardiovascular system is suddenly inadequate for the demands being placed on it. Standing up requires pumping blood upward against gravity again, but your heart is weaker and your blood vessels are less responsive. This orthostatic intolerance, the inability to maintain blood pressure when standing, can be severe. Some astronauts can't stand for more than a few minutes after landing without feeling faint. Research missions on the ISS have tested various countermeasures, lower body negative pressure devices that pull blood toward the legs during exercise, simulating some of gravity's effects. Fluid loading before return to Earth, drinking large amounts of water and salt to temporarily increase blood volume, compression garments that prevent blood pooling. These help, but they don't completely prevent cardiovascular deconditioning. For a Mars mission, cardiovascular health becomes even more critical because the astronauts need to be functional when they arrive. After 6 to 9 months in microgravity during the trip to Mars, they'll experience Martian gravity, which is about 38% of Earth's gravity. That's better than nothing, but it's still a significant adjustment. And if the crew arrives weak and deconditioned, their ability to perform the demanding tasks of establishing a base and conducting exploration is compromised. Mars gravity presents its own interesting challenge. It's strong enough to provide some of gravity's benefits, potentially slowing bone loss and muscle atrophy compared to complete microgravity. But is it enough to maintain long-term health? We genuinely don't know. No human has ever experienced partial gravity for extended periods. The Moon's gravity is about 1/6 of Earth's, and Apollo astronauts spent at most 3 days on the lunar surface, not long enough to see significant physiological changes. Some researchers worry that partial gravity might be worse than microgravity in some ways. In microgravity, your body makes clear adaptations. Everything shifts to a new equilibrium. But in partial gravity, your body might constantly try to maintain Earth normal function and fail, creating a state of chronic stress and incomplete adaptation. It's speculation at this point, but it's a question we need to answer. Here's another aspect of deep space survival that combines biology and physics in unexpected ways: cosmic rays and their effects on vision. We talked earlier about radiation damaging DNA and increasing cancer risk, but high-energy particles can also create strange visual phenomena. Astronauts, even with their eyes closed, report seeing flashes of light. These aren't external lights, they're caused by cosmic rays passing directly through the eye, striking the retina or the optic nerve, and creating a false signal that the brain interprets as light. This might sound harmless, just a weird curiosity of spaceflight. But imagine trying to sleep while random flashes of light interrupt your darkness every few minutes. It's another factor contributing to sleep disruption, another small stressor that compounds with all the others. The cumulative nature of these stressors is really important to understand. No single challenge we've discussed is necessarily unsurmountable on its own, We have countermeasures for radiation. We have exercise protocols for bone and muscle loss. We have psychological support for mental health. We have engineering solutions for life support and thermal control. But throw all these challenges together, operating simultaneously over years, and the cumulative burden becomes immense. It's like asking someone to run a marathon while solving complex math problems, having a conversation in a foreign language, and juggling all at the same time. Each task individually is manageable with training, but doing them all simultaneously is exponentially harder. That's what astronauts face in deep space. Managing radiation exposure while maintaining physical fitness, while keeping life support systems running, while maintaining mental health, while conducting scientific research, while preparing for emergencies. It never stops. There are no days off for years. Let me tell you about something called the overview effect, because it's important for understanding the psychological impact of deep space travel. When astronauts see Earth from orbit for the first time, many report a profound shift in perspective. They see our planet as a fragile blue sphere floating in the blackness of space with no visible borders, no evidence of the conflicts and divisions that dominate human affairs. They see the thin atmosphere, the only thing protecting billions of lives from the hostile void surrounding us. This experience can be deeply moving and transformative. Astronauts often return from space with a renewed sense of Earth's preciousness and humanity's interconnectedness, but there's a flip side. As Earth shrinks to a point of light during a Mars mission, as you watch your home planet disappear into the vastness of space, what does that do to your psyche? You're more alone than any human has ever been, farther from help than any explorer in history. Some psychologists worry about a reverse overview effect, where instead of feeling connected to Earth and humanity, astronauts might feel abandoned, insignificant, overwhelmed by the scale of the cosmos and their isolation within it. We've seen hints of this in analog missions and long-duration stays on the ISS, but nothing comparable to what a Mars crew would experience. The communication delay compounds this feeling. In the early stages of the mission, you can still have somewhat normal conversations with Earth with only a few seconds of delay. But as you travel farther, as minutes turn into tens of minutes between question and answer, Earth feels increasingly distant and disconnected. By the time you reach Mars, you're on your own in a way that no human has ever experienced. Now I want to talk about something that doesn't get enough attention: the sheer duration of exposure to all these stresses. The human body is remarkably adaptable. It can handle short-term extreme stress amazingly well. Soldiers in combat, athletes in competition, people in emergencies, all demonstrate incredible resilience when pushed to their limits for brief periods. But chronic stress is different. When your body's stress response systems are activated continuously for months or years, they start to break down. Cortisol levels become dysregulated, inflammation increases throughout the body, the immune system weakens, mental health deteriorates. We see this in people experiencing chronic stress on Earth, from poverty, abuse, chronic illness, or other long-term hardships. A Mars mission represents the ultimate chronic stress environment. You're never truly safe. You can't relax your vigilance. Every system around you could fail. The environment outside would kill you instantly. Your body is deteriorating despite your best efforts. You're isolated from everyone except your small crew. This continues day after day after day for 3 years. What does that level of chronic stress do to human physiology and psychology over such an extended period? We have some data from extreme environments on Earth, submarines on long deployments, Antarctic research stations during winter isolation, but these are imperfect comparisons. Submariners can surface if there's an emergency. Antarctic researchers know that summer will eventually come and they can leave. Mars astronauts have no such reassurance. There's a concept in stress research called allostatic load, the cumulative burden of chronic stress on the body. High allostatic load is associated with cardiovascular disease, metabolic disorders, immune dysfunction, cognitive decline, and reduced lifespan. A multi-year Mars mission would impose allostatic load that's probably off the charts compared to anything we've studied systematically. And here's something that really makes you think about the depth of this challenge. We're not just asking astronauts to survive the journey, we're asking them to be highly functional when they arrive, landing on Mars, setting up habitats, conducting exploration, troubleshooting problems. All of this requires peak mental and physical performance. If the crew arrives debilitated by the journey, the entire mission could fail even if they survived the transit. This is why some researchers advocate for artificial gravity as the single most important technology we could develop for deep space exploration. If you could create Earth normal gravity or even partial gravity inside the spacecraft during transit, you'd eliminate or dramatically reduce bone loss, muscle atrophy, cardiovascular deconditioning, fluid shifts, and many other physiological problems. The classic design for artificial gravity is a rotating spacecraft. Spin a cylinder or wheel fast enough and centrifugal force pushes everything toward the outer rim, creating the sensation and physical effects of gravity. This concept has been around since the early days of space exploration. Wernher von Braun's famous space station designs from the 1950s featured rotating wheels. Science fiction has explored it endlessly. So why don't we have rotating spacecraft? The engineering challenges are significant. You need a large radius to create comfortable artificial gravity without excessive Coriolis forces. Coriolis forces are the apparent deflection you experience in a rotating reference frame. Move your head in a rotating spacecraft and the Coriolis effect can make you dizzy and nauseous. The larger the radius, the slower you can rotate to achieve the same gravity level, and the smaller the Coriolis forces become. To create one Earth gravity with minimal Coriolis effects, you'd need a radius of at least 50 to 100 meters. That's a big structure, far larger than any spacecraft we've built. The stresses on a structure that large, rotating, to create artificial gravity are substantial. You need strong, lightweight materials. You need bearing systems that can operate continuously for years without maintenance. You need to balance the mass distribution perfectly so the rotation stays stable. Then there's the complexity of having both rotating and non-rotating sections. Docking spacecraft, solar panels, communication antennas, these don't work well if they're spinning. So you need a non-rotating hub connected to the rotating habitat through bearings or other interfaces. Transferring between rotating and non-rotating sections requires careful design to prevent accidents. Despite these challenges, artificial gravity might not just be desirable, it might be essential for Mars missions and beyond. Some researchers argue that without artificial gravity, we simply can't send humans safely to Mars with current physiological knowledge. The health impacts would be too severe, the risks too high. NASA has studied artificial gravity concepts extensively. Small-scale tests have been conducted, spinning astronauts in centrifuges on Earth to simulate the effects. But we've never built or tested a rotating artificial gravity spacecraft in orbit. It's one of those technologies that's been perpetually 20 years away for the past 70 years. Part of the reason is cost and complexity. Every space mission is expensive and risky. Adding the complexity of a rotating spacecraft increases both cost and risk substantially. And until recently, there wasn't an urgent need. The ISS operates in microgravity with astronauts serving 6-month tours. We've learned to manage the health effects for missions of that duration. But a Mars mission is different. The duration and the impossibility of emergency return change the calculation. Let me shift gears and talk about something that sounds mundane, but is actually fascinating and critical: waste management. Humans produce waste, solid and liquid, and in space, you can't just flush it away. early spacecraft had very basic systems. Apollo astronauts dealt with bags and tubes in conditions that were uncomfortable and undignified. The space shuttle improved things with a toilet that used airflow instead of gravity to collect waste. The ISS has relatively sophisticated waste management systems, but they still require maintenance and occasionally fail in unpleasant ways. Solid waste is collected, dried, and stored in containers that are eventually loaded onto cargo ships and burned up during atmospheric re-entry. Urine, as mentioned earlier, is processed and recycled into drinking water. For a Mars mission, you need extremely reliable waste management for 3 years. System failures aren't just unpleasant, they're potential health hazards. Waste contains bacteria and other pathogens. In a closed environment, contamination could spread quickly. Moreover, waste represents resources. Researchers are exploring ways to process human waste to extract water, nutrients that could fertilize plants, and even raw materials for manufacturing. There's serious research into what's called a bioregenerative life support system, where waste products become inputs for growing food. Plants consume carbon dioxide and produce oxygen. They can absorb nutrients from processed waste. Ideally, you create a closed loop where nearly everything is recycled, mimicking Earth's biosphere on a tiny scale. But biological systems are complex and unpredictable. Plants can get diseases, bacteria populations can shift in unexpected ways. Getting a stable, closed-loop ecosystem to function reliably for 3 years in a spacecraft is an enormous challenge. Most researchers think hybrid systems combining mechanical and biological components are more realistic for near-term missions. Here's another thing people rarely consider: what happens if someone dies during the mission? It's a grim topic, but it's a real possibility on a multi-year deep space mission. Medical emergency, accident, radiation-induced illness, any number of causes could result in a crew member's death far from Earth. You can't perform a traditional burial in space. Returning the body to Earth isn't practical. Storing a body for months or years poses hygiene and psychological challenges for the surviving crew. Some researchers have proposed freeze-drying the remains or other preservation methods that minimize mass and eliminate biohazard concerns. But imagine the psychological impact on the crew continuing the mission with their deceased crewmates' remains stored somewhere in the spacecraft. This is the kind of scenario that mission planners have to think about, even though it's uncomfortable. You need protocols. You need to prepare the crew psychologically for this possibility. You need equipment and procedures that preserve dignity while addressing practical concerns. It's space exploration at its most sobering and human. Now let's talk about something that combines all these challenges in a particularly difficult way: medical emergencies. We touched on appendicitis earlier, but the range of potential medical issues is vast. Broken bones from accidents in microgravity, kidney stones from bone calcium loss, infections, cardiovascular events, dental emergencies, psychological crises. Space medicine has advanced considerably over the decades. The ISS has medical equipment and protocols for handling a range of emergencies. Astronauts receive medical training before their missions. But there's a fundamental difference between managing emergencies on the ISS, where definitive care is hours away on Earth, and managing them on a Mars mission, where you are the definitive care. Telemedicine will play a critical role. Despite communication delays, doctors on Earth can review data, examine images, and provide guidance to the crew. But performing complex procedures based on delayed instructions is incredibly challenging. Imagine trying to suture a wound or set a broken bone while following instructions that are 20 minutes out of date. Research is ongoing into autonomous medical systems, artificial intelligence that can guide crew members through procedures, robotic surgical systems that could assist with operations, advanced diagnostics that work in the space environment. But we're still years away from having truly autonomous medical capability that doesn't rely on Earth-based expertise. There's also the question of medical consumables. Bandages, medications, sterile supplies all have shelf lives. Some medications degrade faster in the space radiation environment. You need to carry enough supplies for 3 years, including reserves for emergencies, but you can't carry infinite quantities. And if you run out of a critical medication, there's no resupply coming. Antibiotics are particularly concerning. Bacteria in space have been shown to become more virulent and more resistant to antibiotics. The stress of the space environment, the recycled air and water, the close quarters, all create conditions where infections could spread rapidly. If a resistant infection takes hold in the crew and your antibiotics are ineffective, you could face a life-threatening situation with no good options. Let me tell you about something that keeps coming up in discussions about long-duration spaceflight: the question of crew size. You might think that bringing more people would be better, more hands to share the workload, more expertise to handle problems, more social interaction to prevent isolation. But it's not that simple. Every additional crew member requires life support, food, water, living space, and all the associated systems. Mass increases, which means more fuel is needed, which increases cost exponentially. There are diminishing returns. A crew of 12 isn't necessarily better than a crew of 6. It's just more expensive and complex. But a crew that's too small faces different problems. If you have only 4 people and one becomes incapacitated, you've lost 25% of your capability. You don't have enough redundancy in skills. If your only person with medical training becomes the patient, who treats them? If your engineer gets injured, who maintains the systems? Studies suggest that 6 to 8 people might be optimal for a Mars mission, large enough to have skill redundancy and healthy group dynamics, small enough to keep resource requirements manageable. But even determining optimal crew size requires assumptions about mission architecture, available technology, and acceptable risk levels that we're still debating. Crew composition is equally important. What skills do you need? Pilots, engineers, medical professionals, scientists, geologists for Mars surface work. Everyone needs to be cross-trained in multiple areas because specialization is a luxury you can't afford when there are only 6 of you. The ideal Mars astronaut is a polymath, medically trained, mechanically skilled, scientifically literate, psychologically resilient, physically fit, and socially compatible with the rest of the crew. Finding 6 to 8 people who meet all those criteria and can work together effectively for 3 years is extraordinarily difficult. Space agencies spend years selecting and training crews for 6-month ISS missions. The selection process for a Mars crew would be even more intensive, and there's the question of gender composition. Early space programs were male-dominated, but we've learned that diverse crews often perform better. Different perspectives and approaches to problem-solving can be crucial in unexpected situations. Research on analog missions suggests that mixed-gender crews may handle the psychological stresses of isolation better than single-gender crews, though the data is still limited. But mixed-gender crews introduce other considerations. Sexual relationships, pregnancy prevention, and interpersonal dynamics all become factors in mission planning. These are sensitive topics, but they're real concerns when you're sealing people in a spacecraft for 3 years. NASA and other space agencies have policies prohibiting sexual relationships during missions, but enforcing such policies over 3 years of isolation would be challenging. Some researchers argue that it's unrealistic to expect human beings to suppress natural desires for that long, and that attempting to do so might create more psychological problems than it solves. Others maintain that professionalism and mission focus should prevail. The pregnancy question is particularly serious. Pregnancy in deep space would be extremely dangerous. We have virtually no data on how radiation exposure and microgravity would affect fetal development. Animal studies suggest that both factors could cause severe developmental problems. The medical demands of pregnancy and childbirth would strain the mission's capabilities. Most space agencies consider preventing pregnancy during deep space missions an absolute requirement. These human factors, the messy biological and psychological realities of being human, are in many ways harder to solve than the engineering challenges. We can design better radiation shielding, improve life support systems, develop artificial gravity, but we can't redesign human nature. We have to work with the biological and psychological hardware evolution gave us, even though it wasn't designed for the environment we're asking it to function in. Let me share something that really illustrates how much we still have to learn. In 2015, astronaut Scott Kelly spent nearly a year on the ISS while his identical twin brother Mark, also an astronaut, remained on Earth. This twin study provided a unique opportunity to examine the effects of long-duration spaceflight with a perfect genetic control. The results were fascinating and concerning. Scott experienced changes in gene expression, with hundreds of genes turning on or off differently than Mark's. His telomeres, the protective caps on chromosomes that typically shorten with age, actually lengthened in space, then rapidly shortened after return to Earth. His carotid artery thickened. His cognitive function showed some decline. Most changes reversed after returning to Earth, but not all. Some alterations persisted for months or years. 1 year in space, with most of that time on the ISS protected by Earth's magnetosphere, caused measurable changes at the genetic and cellular level. What happens after 3 years in deep space with full cosmic radiation exposure? We can make educated guesses, but we don't really know. The first crew to Mars will, in a very real sense, be guinea pigs in an experiment that's never been run before. This brings us to an uncomfortable ethical question. Is it responsible to send humans to Mars given the risks and unknowns? Some argue that informed adults should be free to accept risks if they choose, and that exploration has always involved danger. The first sailors to cross oceans, the first climbers to attempt Everest, the first aviators, all faced risks that were poorly understood at the time. Others argue that we have a responsibility to minimize risks to the greatest extent possible before attempting a Mars mission, even if that means waiting decades for better technology and more knowledge. They point out that a catastrophic failure wouldn't just kill the crew, it could set back space exploration by a generation or more, just as the Challenger and Columbia disasters temporarily grounded the shuttle program. There's no easy answer, but I think most people involved in space exploration would say that we need to be honest about the risks while continuing to work on reducing them. Pretending deep space is safer than it is serves no one. But abandoning the goal because it's difficult isn't acceptable either. Here's something that gives me hope despite all these challenges: human ingenuity and adaptability. When faced with seemingly impossible problems, we figure things out. The Apollo 13 crew and mission control improvised solutions to problems that had never been anticipated. Engineers designed a carbon dioxide scrubber adapter using only materials available on the spacecraft: duct tape, cardboard, plastic bags, and hoses. It worked. It saved their lives. That same ingenuity will be essential for Mars missions. You can't anticipate every problem. You can't pack a spare part for every possible failure. At some point, you're relying on smart, resourceful people to solve novel problems with limited resources under extreme pressure. And humans, for all our biological limitations in space, are remarkably good at that. We're also developing technologies specifically designed to help. 3D printing could allow crews to manufacture tools and spare parts from raw materials rather than carrying everything from Earth. Advanced materials that are stronger and lighter reduce mass requirements. Improved computing and artificial intelligence can assist with diagnostics and decision-making. Better understanding of radiation biology might lead to pharmaceutical countermeasures that reduce DNA damage. Each incremental improvement makes deep space exploration a little more feasible. None of them individually solves the problem, but collectively they're moving us closer to making Mars missions survivable, not just theoretically possible, but actually achievable with acceptable risk. The International Space Station has been humanity's proving ground for long-duration spaceflight for over 2 decades now. We've learned an enormous amount. Every mission adds to our knowledge. Every experiment provides data. Every challenge encountered and overcome teaches us something valuable. The ISS isn't just a research laboratory, it's a training ground for the technologies, procedures, and human factors knowledge we'll need for Mars. And beyond Mars, what then? If we can solve the challenges of a 3-year Mars mission, we open up the solar system. Asteroids rich in valuable minerals, the moons of Jupiter and Saturn with their subsurface oceans, potential harbors for life. Eventually even interstellar space, though that presents challenges that make Mars look easy by comparison. But I'm getting ahead of myself. The immediate challenge is Mars, and it's enormous. Everything we've discussed, radiation, bone loss, muscle atrophy, psychological stress, life support challenges, medical emergencies, the cumulative chronic stress of years in a hostile environment, these aren't abstract problems, they're real barriers that need real solutions. The question isn't whether humans will eventually reach Mars and survive. I think we will. The question is when and at what cost. Will the first mission succeed or end in tragedy? Will we develop the technologies and countermeasures needed to make deep space exploration sustainable, or will we push forward with current capabilities and accept higher risks? These are questions without clear answers yet. But thinking about them, understanding the real challenges, that's how we move from fantasy to reality. Space exploration isn't a magic solution or an easy escape. It's hard, dangerous work that will push human capabilities to their absolute limits. And if you find these challenges as fascinating as I do, if you wonder about the obstacles that lie between humanity and the stars, then you might want to explore another mystery that connects to all of this. The Fermi paradox has a terrifying solution. If space is so hostile, so fundamentally deadly to biological life, what does that mean for other civilizations out there? Watch that video on the screen to dive deeper into one of the most unsettling questions in all of science. See you there.